techniques, if you have an interesting result about Hilbert-Samuel polynomial, you ask the same question for Hilbert-Kunz function. And many times you get exactly the same result, but many times there are differences. And it may not be possible to answer. So I have taken a few samples of results in classical theory like Nagata's theorem to compare the results for Hilbert-Kunz multiplicity and the older results. Then towards the end, I will report on recent research about Hilbert-Kunz multiplicity of powers of an ideal, which is an attempt to calculate the Hilbert-Kunz multiplicity of powers using Hilbert-Samuel polynomial. One problem about Hilbert-Kunz multiplicity is that one cannot calculate using induction. There is no way of going down to the dimension, and in dimension 1 and 2, many things are very easy to calculate, but in higher dimension, things become very complicated. But there is no inductive device to calculate the Hilbert-Kunz multiplicity. Unlike the classical multiplicity of a local ring, where we can use superficial elements and reductions, and there are lots of techniques you can come down to dimension 1 and flip the situation back about multiplicity. Okay. And this question that I'm going to discuss of here now, it relates Hilbert-Kunz multiplicity with the Hilbert-Samuel coefficients of Frobenius powers of the ideal. So if this conjecture is true, it will help us to calculate Hilbert-Kunz multiplicity of powers again using the classical methods of Hilbert-Samuel multiplicity. And I will show how this conjecture is true in many situations. The complete conjecture is still not solved. Okay. So that is the plan of the talk. Yeah. So let me begin by recalling these concepts from 1950s introduced by Northcott and Rees, reductions and integral closure of ideals. So I and J are ideals of a commutative Noetherian ring. Yeah. So yeah, I need a stick. This light is not working on this. Is there a way to bring some pointer like hand or something? Okay. Then I have to operate here.
Yeah, can it be here?
I will manage. Yeah. So we have two ideals, I and J. J is contained in I, so that we have this relation, JIN is n plus 1 for some n and hence for all large n. Then J is called a reduction of I. It's a simpler version of the ideal, which is good, very good for computing Hilbert-Samuel function. The smallest reduction of I with respect to containment is called a minimal reduction of I. And if the residue field is infinite, there are infinitely many minimal reductions. But all of them require same number of generators, and that number of generators is called the analytic spread of the ideal. It is the dimension of the to blow up the ideal. I mean, spec R with respect to the closed subset Pi, variety of I, and take the fiber of the closed point. That dimension of that fiber is the number of generators of any minimal reduction of the given ideal. Okay. So that's the concept of minimal reduction. It is very useful to calculate multiplicity. The reduction number of the ideal with respect to this minimal reduction, this reduction is the smallest n, so that this is true. A closely related concept is that of integral closure. So suppose we have a commutative ring and I is an ideal. An element A in R is called integral over this ideal if there are elements AI in the ith power. So that we have this monic polynomial equation satisfied by X. So unlike the equation for integral closure of an element in a ring, these coefficients have to be in the right power of the ideal. Then it is called integral element over I. And if you collect all the elements which are integral, that set itself is an ideal, and that is called the integral closure of I. And from definition, it is clear that it is contained in radical of I. So if you took a prime ideal or a radical ideal, then the ideal is its own integral closure. And whenever this happens, we say it's a complete ideal. Yeah. So this terminology is due to Zariski. There is a result of Northcott and Rees. R is a ring, J containing I are ideals. Then J is a reduction of I, okay, if I is integral over G. So if you remove integral elements from an ideal and look at a sub-ideal, that is going to be reduction. And you want to simplify more, so remove more and more elements that are integral. Okay? But the experience shows that if you attach integral elements, the ideal becomes better and better. Just like normal rings are better. Complete ideals are better than the usual ideals. Here is a classical result of Zariski from 1938. That product of complete ideals is complete in polynomial ring over a field which is algebraically closed of characteristics. Yeah. So prime ideals are complete and maximal ideal is complete, but this says that there are lots of complete ideals. You multiply them, you get complete. Okay. Yeah. And this theorem was generalized to two-dimensional regular local ring in Alexis Samuel Commutative Algebra, Appendix 5, Volume 2. Okay. If you have gone that far, there is a beautiful proof of this for any two-dimensional regular. Yeah. So, all right. Recall Hilbert-Samuel multiplicity of an ideal. So we have M primary ideal in a local ring. All my rings are Lorentzian. Then the Hilbert-Samuel function is the co-length of the nth power. So as n varies, this function becomes a polynomial for large n. And we write Hilbert polynomial in this as a linear combination of integer combination of these binomials. It's an integer value polynomial, so we can write an integral combination and write in alternating fashion. Then these integers, ei, e1i, edi, these are called the Hilbert-Samuel coefficients of this ideal. And these coefficients have information about the local ring. Especially when the ideal is the maximal ideal, then the coefficients of Hilbert polynomial, they can tell a lot about the local ring and other rings which are associated with R. Okay. So EI is of course the classical multiplicity of I, which is a measure of the singularity of the given local ring. This condition comes up all the time. So this is called, a local ring is called unmixed or also called formally unmixed if every associated prime of the completion, MID completion of R has the same dimension as the dimension of the ring. Okay. Sometimes there are other components which are not of that dimension. Those components don't contribute to the multiplicity. Okay. So that is why, and multiplicity doesn't change if you complete the local ring. Okay. So that is why it's a natural condition to impose if you want to calculate this. Northcott and Rees proved that if J is a reduction of I, then multiplicities are same, and therefore it is useful to calculate multiplicity of the original ideal because you can pass to a ideal which is generated by system parameters where multiplicity is easier to calculate and without changing the multiplicity. And the converse is true if the ring is an unmixed property. Okay. Yeah. All right. Nagata's theorem about regular local ring. So take a d-dimensional regular local ring. Then the associated greater ring is a polynomial ring in d variables. And therefore, we can easily calculate the Hilbert-Samuel function of maximal ideal. And that is this binomial n plus d minus 1 d. That's the number of monomials in d variables of degree at most n minus 1. So Hilbert-Samuel polynomial is very easy to calculate. And so therefore, multiplicity is 1 and the other coefficients are all 0. So that is the best situation you can have for computation of Hilbert-Samuel polynomial. Converse of this term is not true. That is, this multiplicity being 1 doesn't say that the ring is a regular local ring. Doesn't say that the point is smooth. Okay. Although multiplicity could be the smallest possible value. And what goes wrong is the unmixedness property. So take this quotient. There are two minimal primes in this complete local ring of different dimensions. One dimension is 2 and another dimension is 1. And here the multiplicity is 1, but the ring is not, certainly not a double. It's a reduced ring. It's not even an integral ring. So the unmixedness hypothesis is always there if you want to conclude anything about the a local ring from the multiplicity. Okay. So ring is regular local ring if and only it is unmixed and the multiplicity. You will see that exactly same theorem is true for Hilbert. And can characterize 2 points. The lowest value of the multiplicity gives you a point on the ring. So this was the inspiring result for that. Yeah. So let me now introduce Hilbert function and its relation with regular local ring. Take a local ring of prime characteristic P. Okay. So P is always positive, and Q equal to a power of P. And take an ideal, then the Qth Frobenius power is the ideal which is generated by Qth power of the generators of I, and it is independent of how you write these. So it's a image of the Frobenius map of J. Okay. So just raise the generators to Qth power, that is called the Frobenius power. And how the Frobenius powers grow helps us to understand the local ring. So just like Hilbert Samuel function, here we have Hilbert function, which is co-length of the Frobenius power. Phi is M primary, Frobenius power is also M primary. So this length makes sense. And this is a function of Q. But unlike Hilbert Samuel polynomial, for large Q, this is rarely a polynomial. It can be a very complicated function, this Hilbert function, but we can extract an analog of classical multiplicity from this function, fortunately. So Kunz was the first one. He was in the 60s. He looked at this function and mentioned that it may not exist. This limit may not exist. And then nobody worked on it. Everybody believed Kunz until Monsky approached the same limit while looking at it. This is on ideal class groups in number theory in characteristic P. And there, the computation of torsion in ideal class group in characteristic P gives rise to the same function. But because of motivation from number theory, he always believed that this limit exists. And he gave a proof and told Heisenberg that this function is there and it seems the limit exists, but Kunz is saying, then Heisenberg said, but you say Kunz said that this limit doesn't exist, and he had a counterexample. But Monsky, being Monsky, he stuck to his guns and he proved that this limit does exist. That gave rise to lots of developments. So Kunz himself considered this function and showed that for any local ring of dimension D, this function has a lower bound, which is Q to the power D. D is the dimension. Okay. This is similar to the Hilbert Samuel function. Yeah, there also the Hilbert Samuel polynomial is a polynomial of degree D. Okay. But here the maximum power of Q which comes to this function is still Q to the D. And so he wondered when this lower bound is achieved. Okay. So then he proved that the lower bound is achieved for some Q if and only if the ring is general. So that's a criterion, corresponding criterion. And you can easily show, because a regular local ring is a confocal ring, and maximal ideal is generated by a regular sequence of length D. So therefore, this length you can easily calculate, that is equal to Q to the D. And therefore, you divide by QD and take the limit, the Hilbert multiplicity is 1, and that is the smallest possible value that you can have for Hilbert multiplicity. And this characterizes regular local rings. So if you have a regular local ring of prime characteristic, then also using the Kunz also proved that in characteristic P, the Frobenius map is a flat map if the ring is regular local ring. It's a characterization of regularity. So using that, you can easily show that the Hilbert-Kunz multiplicity of any primary ideal regular local ring is just the co-length of pi. So computation of Hilbert-Kunz multiplicity regular local ring is a trivial affair, okay, because you just calculate the length of pi. Yeah, only when you go to actual similarity, the computation becomes trivial. And it can be an irrational number. That's another complication. Yeah. It can be an irrational number. Yeah. But in many situations, it turns out to be a rational number. Yeah. All right. This is the relation with classical multiplicity, that for any primary ideal, the Hilbert-Kunz multiplicity of I is bounded below by EI over D factorial, bounded above by EI. So if you take one-dimensional local ring, then they become equality, and again, so in one-dimensional local ring, computing Hilbert-Coon multiplicity is same as computing the multiplicity of the ideal. Yeah. So the difference starts coming in dimension bigger than 1. The dimension 1 EI is same as ESK of I. Yeah. Then this is the analog of Nagata's theorem that unmixed local ring is regular if and only Hilbert-Coon multiplicity of maximum ideal is 1. The exact parallel law of Nagata's theorem is for Hilbert-Coon multiplicity and characterization of regular. This proof is not that easy. It takes some time to prove. HK multiplicity is related with tight closure in a very crucial way. Let me recall definition of tight closure. We have minimal primes, list all the minimal primes of a ring and take their complement, which is RO. For an ideal thing, tight closure is collection of all elements X, so that there is a C in RO, so that CX cube belongs to the Frobenius power for large. Yeah. So these are infinitely many equations. Okay. It's difficult to check. Okay. Infinitely many equations whether this belongs to this ideal or not. Okay. So computation of tight closure can be difficult, but it is closely related with Hilbert-Coon multiplicity. This is a result of oxidation unity. That if you take a regular local ring, then all ideals are tightly closed. I is equal to I star. Okay. So because of that, since I equal to I star, okay, this result will say that if you want to prove that some element is in an ideal, this is often many questions they reduce to deciding whether something is in a given ideal. Yeah. Ideal membership problem. As you know, in Grobler basis, that is a fundamental question to decide whether a given polynomial is in a given polynomial. What this is saying that if you take a regular local ring, and because I equal to I star, this criterion tells you when a given element is in the ideal. And so that's why computation can be difficult, but in a regular local ring, if you show that some element is in tight closure, it becomes easier to prove that it is actually in the ideal. It may be difficult to prove that the given element belongs to the given ideal, but it may be easier to prove that it is in the tight closure of the ideal. So many results, classical results are proved by, in regular local ring are proved by using this philosophy that results show that the given element is in the tight closure. Yeah. So, and if you have two ideals, M primary ideal, one is contained in I, which have same tight closure, then the Hilbert-Coon multiplicity is the same. So this is exactly analogous to the result for integral closure. If two ideals have the same integral closure, then multiplicity is the same. That so integral closure is replaced by tight closure and multiplicity is replaced by Hilbert-Coon multiplicity. If R is unmixed local ring, the converse is also true. If I have one ideal contained in this ideal and they have same Hilbert-Coon multiplicity, then they have same tight closure. So this is useful to many times to prove that given element is not in the tight closure. Somehow you calculate their Hilbert-Coon multiplicity and show that they are not equal. Then the given element will not be in the tight closure. So now I recall this definition that Mitra had defined 4 types of similarities in characteristic P. One of them is called weakly F regular. So these are rings, local rings of prime characteristic where all ideals are tightly. So these are called weakly F regular. Okay. And F regular are those rings where all localizations are weakly F regular. And right now one doesn't know whether there is a difference between them. Whether the weak F regularity localized, whether this property passes on to localization. So that is an open problem. Yeah. Now I have to recall a few results which show that the value of HK multiplicity alone has a strong influence on the structure of the local. So here is one result of Watanabe and Ishida. Take a Cohen-Macaulay ring of multiplicity 2. So if the ring is not a regular local ring, then this is the next best value of the multiplicity. That is, so you take a double point of a hypersurface, then its multiplicity is 2. So if you have a Cohen-Macaulay ring of multiplicity 2, then the Hilbert-Coon multiplicity being 2 characterizes whether the ring is a weakly F regular. So just this number equal to 2 tells you that all ideals are tightly. Yeah. So if the Hilbert-Coon multiplicity is 1 and the ring is unmixed, then the ring is a regular local ring, and so all ideals are tightly. So regular local rings are weakly regular, but this is a larger class than regular local ring, and this shows that to take a double point of a hypersurface in dimension 2, I mean actual surface of dimension 2, then it is a weakly regular local ring. So it's a bigger class than the regular local ring. Take a dimension 2 Cohn-Macaulay ring, and then the Hilbert-Cohen multiplicity is bounded below by ER plus 1 always. Yeah. So this is a lower bound on Hilbert-Cohen multiplicity. And if the lower bound is achieved, then the singularity is usually better. Just like regularity is characterized by smallest value of SK multiplicity. If the ring, so if its dimension is 2, then this is a lower bound. And they proved that if the residue field is algebraically closed, then the lower bound is achieved if and only if the associated graded ring is the Veronesian eth Veronesian power of Tx. So this tells you the entire Hilbert polynomial of the associated graded ring. It becomes a Veronesian subring, so it means the tangent cone is very nice in this situation. So lower bound on Hilbert-Cohen multiplicity used in the structure of the singularity. It's tangent cone. Okay. This happens in many other situations. So here is a conjecture of Watanabe and Yoshida from 2001. Take an odd prime and then D at least 1, and look at this quadratic hypersurface. The completion of the local ring at the origin of this quadratic hypersurface is a d-dimensional ring, and it is over the algebraic closure of finite field P. Okay, so call this ring as RPD. Then take a unmixed local ring of dimension D, so that the residue field is algebraically closed of characteristic D, and let AD be the coefficient of x to the d in the Taylor series expansion of this trigonometric function secant x plus tangent x. Yeah, so take the its Taylor series expansion around 0, x equal to 0, and let AD be its coefficient. Then if R is not regular, then Hilbert-Cohen multiplicity is bounded below by Hilbert-Cohen multiplicity of this hypersurface. So you see, on one side I have arbitrary unmixed local of dimension d. Okay, any unmixed local of dimension d. Then it is saying that there is a lower bound on its Hilbert-Cohen multiplicity, and that lower bound is the Hilbert-Cohen multiplicity of this quadratic hypersurface. And this is bigger or equal to 1 plus this number. This is the coefficient of x to the d in the Taylor series expansion. Yeah. So this looks like a very nice thing to experiment with, but it is quite difficult to calculate its Hilbert-Cohen multiplicity. Okay. If the other part of the conjecture is that if this becomes equal, if Hilbert-Cohen multiplicity is equal to the Hilbert-Cohen multiplicity of this ring, then the completion of the local ring is isomorphic to this ring. So this is a very strong structural theorem. You don't expect R to be isomorphic to this, because under completion Hilbert-Cohen multiplicity doesn't change. So at most you can say about R completion. So R completion is isomorphic. Yeah. So just one number decides whether this is true. This is still open, but Trivedi recently proved that the part 1 of the conjecture, which gives these inequalities, that is true if P is bigger than P constant. Yeah. So for large primes, the conjecture is true. In fact, using our theory of Hilbert-Cohen's density function, she gives a closed formula for Hilbert-Cohen's multiplicity here, and which involves 1 plus AD plus certain quotient of polynomials. Yeah. And then she proves that if P is approaching to infinity, then this number is approaching to this number. And there is an error term which she finds out, and she makes use of geometric techniques. In particular, she is using that the classification of vector bundles on quadratic hypersurfaces, that they are related with some matrix factorization. So very different techniques are used in actual computation of Hilbert-Cohen multiplicity. Here is another characterization. Take a unmixed local ring, which is a homomorphic image of a Cohn-Macaulay. So, for example, if you have a complete local domain, then both these conditions are satisfied. Take a parameter ideal, that is ideal by system parameters. Then the length of R mod the tight closure is a lower bound on You see, there are many lower bounds given here. And this is saying that this is always bigger than 1. So the question is, if this lower bound is achieved, what can you say about the local ring? Okay, that is usually the question in all these lectures. So equality holds if and only if the given ring is F-rational. F-rational ring is that in which all system of parameters or all parameter ideals are tightly closed, rather than all ideals. That those are called VTF regular. But F-rational similarity is the one in which all parameter ideals are tightly closed. And if the Hilbert multiplicity coincides with the core length of I star, then it is F-rational. So this is another instance that how the nature of the singularity is decided by the value of the Hilbert multiplicity. So now let me come to a recent question about a way of computing the Hilbert multiplicity. So this one would so it's clear that computing Hilbert multiplicity is rather difficult. So one would like to somehow relate it with the classical methods of computing Hilbert sample coefficients. So there, I want to talk about a conjecture of speed law, which precisely does that. It relates Hilbert multiplicity of not just a given ideal but all powers with Hilbert sample coefficients. So let me build up to his question. So take a Cohn-Macaulay local ring and I is generated by system parameters. Then the ideal is generated by a regular sequence, and therefore the Frobenius power is also generated by regular sequence. And if you have an ideal generated by regular sequence, then Hilbert sample function is very simple. It is this the whole length of this ideal times this binomial. And but this is the length of R mod. The fused Frobenius power is multiplicity of Y times T. Okay, that's just from properties of regular sequence. So therefore, the Hilbert sample polynomial of Frobenius power of an ideal generated by system parameters is very nice. It's a polynomial function in N as well as Q. And both the degrees are equal to D. The degree in N is D and degree in Q is also D. And Hilbert sample coefficient is important. Okay. So this is one calculation. But the ideal generated by regular sequence is an ideal of reduction number 0. What about ideals of reduction number 1? So here in this calculation, if I now divide by Q to the D and take the limit, then I will get a formula for Hilbert multiplicity of all powers. It is equal to DI times this one. So we would like to understand the nature of Hilbert multiplicity of powers in terms of coefficients of Hilbert sample polynomial. And this calculation raises the question. Now, so the ideal generated by regular sequence is an ideal of reduction number 0. Go to ideals which have reduction number 1 or 0. An ideal in Gaussian local ring is called stable ideal if for any minimal reduction Ji equal to I square. So this ideal which is generated by regular sequence system parameters, this certainly satisfies this condition, right? Because if you take an ideal generated by regular sequence, then it has no proper minimal reduction. So J equal to I in that case. But there are local rings where the maximal ideal has reduction number not 0 but reduction number 1. So for example, if you take a double point of a surface, then it will have reduction number 1. Or in particular, if you take a two-dimensional rational singularity, then the maximal ideal has reduction. Okay. So we say an ideal is a stable ideal if Ji equal to I square for any minimal reduction. And one can show that this condition is independent of which minimal reduction you choose. There are infinitely many minimal reduction, but once it is satisfied for one minimal reduction, it is satisfied for all. Okay. That gives a little bit too, but it is independent of which minimal reduction. A local ring, Cohn-Macaulay local ring, is set by minimal multiplicity if the embedding dimension plus R is equal to multiplicity. In general, multiplicity is bounded below by this number. So when the minimal value is achieved, and we say the ring has minimal multiplicity or maximal embedding dimension, both are used. Okay. So embedding dimension is just the number of generators of maximal. A ring, Cohn-Macaulay local ring has minimal multiplicity, you can only the maximal ideal is the stable ideal. So as I said, we take a two-dimensional rational singularity, then the maximal ideal is the stable ideal. Or take a double point as the stable ideal. So in this situation, we can calculate Hilbert multiplicity of powers of an ideal. So So take a cone-Macquarrie local ring of dimension at least 2 and let I be a stable ideal. Then because of this relation, one can calculate the Hilbert sample polynomial. This is an old theorem of Northcott, that is Ji equal y square. One can calculate all the coefficients of Hilbert sample polynomial. And if this equation holds, the same equation will hold for any Frobenius power. Yeah, same equation. And therefore, once again, we can apply Northcott's theorem to calculate the Hilbert sample polynomial of every Frobenius power of I also, okay, because the reduction number is still at most 1. And using that formula, one can derive the Hilbert multiplicity of powers as EI times n plus b minus 2 to b minus EI minus Hilbert multiplicity times this. So if I somehow calculate the Hilbert multiplicity of I and EI, then I know from this formula Hilbert multiplicity of all powers. Yeah. Okay. So this is assuming that the reduction number is 1. So in both these situations, you see the EHK of IN involves coefficients of the Hilbert sample polynomial of I and the Hilbert multiplicity. So one can ask, what exactly is happening in a general situation. If you remove the condition that it's a stable ideal, then is there a formula for Hilbert multiplicity of powers of ideal? This involves other coefficients, the Hilbert sample coefficients. So such a question has been asked by Smirnov. So suppose, so it begins with this result of Trivedi from 2017. Take an ideal generated by elements of same degree in a standard. It should be homogeneous ideal in a standard graded ring over perfect field of prime characteristic P. Then look at the first Hilbert sample coefficient. Okay. E0 of the Frobenius power can be determined in terms of the multiplicity. That is easy to do. But take the first Hilbert coefficient, E1 of the Frobenius power, divide by this number and QD and take the limit. Then she proved that this limit exists and this limit is given by this formula. So it involves Hilbert multiplicity of powers asymptotically and multiplicity of IK and these numbers. And so in particular, it says that this limit exists. The limit of E1 of Frobenius power over QD as to the infinity, that number exists and it is related with the Hilbert multiplicity of powers by this formula. Okay. So now this is the question whether the limits of other the Hilbert coefficients of other Frobenius powers also exist. Yeah, that's a natural question to ask, and this is what Smirnov has asked. That take a neutral local ring, I is an M primary ideal. Then so this is the standard graded ring, and I is homogeneous ideal. The degrees of the generators are same. Smirnov proved this in the any neutral local ring. Same result in any neutral local ring. So these are more or less the same results that the multiplicity of IN in any neutral local ring and I is an primary ideal involves EI. It involves asymptotic value of the E1 of the Frobenius powers, and then some other terms here, which are not reveal what they are. But then he asks whether these exist. That is, EI of Frobenius power of QB, does it exist for everyone? It exists for E1, it exists for E0. Does it exist for everyone? Okay. And why does he want to do that? Well, he says that if these limits exist, then EHK of IN should be like the Hilbert sample polynomial, but the coefficients are going to be limiting values of the IN Hilbert coefficient of the Frobenius. Yeah. So if this is still open, but in many cases this is true, but it opens the door to computing EHK of IN using properties of classical Hilbert sample coefficients, which can be computed many times using induction and local cohomology and many other techniques. So if this were true, it will simplify computation of EHK of IN. And why one cares for EHK of I to the n? Because this number as n grows also tells you the nature of the similarity. Not just EHK of I. How EHK of IN grows with n tells you something more about the singularity here. Okay. So how much time I have?
Started late. 8:20.
Oh, that's how much time?
20 minutes.
Okay. All right.
The second is still a question of even asking
It is a question. Yeah, it's not.
even after assuming the
Yeah. Yeah. But I want to point out in many situations. All right. So Smirnov's question, I want to show you that in the phase rings of simplicial complexes, his question has a positive answer. So here we can do some hand computation, and it turns out that it has positive answer. So let me recall what these things are. So take a d-1 dimensional simplicial complex on the vertex set 1 of 2R, and take polynomial ring in R variables. And if F is a facet, that is a phase of maximal dimension in the simplicial complex, then this facet gives me a prime ideal which is generated by those xi so that I is not a vertex space. Okay, so take this prime ideal for each facet. Then if you list all the facets of the simplicial complex, then the ideal of the simplicial complex that's generated by square field monomials, and that ideal is intersection of these facet ideals Pf1, Pf2, Pf1. So that's this ideal is generated by some square field monomials. The phase ring is the quotient of polynomial ring by the ideal of the simplicial complex, and one can show that the dimension, the total dimension of the phase ring is equal to d, and where there is one more than the dimension of this complex. Okay, so that is the phase ring, and then we calculate the input. So take maximal homogeneous ideal of polynomial ring rho mod I delta. I'm writing I for I delta. So take this maximal homogeneous ideal of R. Okay. Then so then look at the maximal homogeneous generators of the maximal homogeneous ideal of the phase ring and raise them to any positive powers you wish. Okay. So in particular, you could take Frobenius powers also, but you can take any positive powers of these generators of maximal homogeneous ideal. Yeah. Then we calculate the Hilbert function of the kth power of this ideal. Yeah. So this is the Frobenius power and ordinary power. They compete with each other. So this can be thought of as the Hilbert function of kth power, or it can be thought of as the Hilbert-Samuel function of the Frobenius power. Both interpretations are valid here. Okay. Then, and we show that the ith Hilbert coefficient of the qth Frobenius power of qd as q is approaching infinity is actually 0 for all I to the 24. So there is only one which is surviving among the asymptotic EIs for this ideal. So all these limits exist. Okay, A0 of this exists. That is easy to show. Okay, because the multiplicity of Frobenius power is same as multiplicity of the ordinary power, because the ordinary power is an integral extension of the Frobenius power. So that multiplicity doesn't change, and multiplicity of a power of a M primary ideal is equal to that power to the power d times the multiplicity. So the question is trivial for E0, but here we are showing that the other limits also exist. That was the conjecture of Smirnov, and in this case, these limits turn out to be 0. And so his second question has a positive answer, that the Hilbert multiplicity of kth power of this ideal is easier times this binomial. Okay, so for phase rings and for the Frobenius powers of maximal ideal in the phase ring, the conjecture is true. Okay, so I want to illustrate the proof in an example. The proof in the general case is very similar to what this is the example we just calculated, and that gives the general proof also. So take one-dimensional simplicial complex on 4 vertices. There's this line. Then there are 1, 2, 3 facets. So take this first edge x1, x2. Its complement is generated by x3, x4. That is the facet ideal of the first edge. Then the second edge, the facet ideal is x1, x4. For the third edge, the facet ideal is generated by the complement, is x1, x2. And the ideal of the simplicial complex is the intersection of these 3 prime ideals. Well, this a quotient, one can easily calculate the inverse series of this quotient by computing an exact sequence. And so that it turns out that the length of R mod kth power of this Frobenius power is this alternating sum, where we go mod pi, here we go mod pi plus pj, and here we go mod all the pi's. Now notice that S is a polynomial ring, and pi's are generated by subset of variables. So S mod pi are polynomial. In polynomial rings, computing the sample polynomial of Frobenius power is easy, because in S mod pi, this Frobenius power is generated by a regular sequence of length 2, and there it's very easy to calculate. So we put together all these computations and see that the Hilbert sample polynomial of this Frobenius power is 3 times k plus 1 over 2 times k squared. So there is no constant term here in k. It's a polynomial in k as well as q. The degree in k is also 2, which is the dimension of the phase ring, and the degree in q is also 2. Okay, so then divide by q square and take the limit, and then we will get that the Hilbert sample multiplicity of this Frobenius power is 3q square, E1 of this is 2q, A2 is 0, and therefore when I divide this by q square, all these things, the limits exist, and EHK of nk is 3 times k plus 1. Exactly same thing is true for any phase demonstration complex, because I can write the Hilbert sample polynomial of Frobenius power as an alternating sum of the Hilbert sample polynomial in polynomial sum polynomial. Yeah. All right. So now let me come to the second question. This I already defined. So for an arbitrary ideal, the associated ring of an ideal is in over in plus 1, and in many situations, the depth of the associated graded ring controls the Hilbert sample coefficients of the given ideal. Okay, suppose this Gi is called. Okay, then so this happens. It's not something very strong, because suppose you take a 2-dimensional rational singularity or a ring with minimal multiplicity, the associated graded ring of maximal ideal is actually 1. So the depth determines coefficients in many situations, and so this is in order to tackle this question, we look at this small class of ideals. Take one ring of prime characteristic, take an M primary ideal, and suppose the depth of the Frobenius power of I is at least d minus 1 for large. Okay. So this is a strong condition, but suppose I have a regular local ring and an M primary ideal regular local ring. Then the depth of the associated graded ring of Frobenius powers are all same. They are all same because of the exactness of the Frobenius. Okay. So one can just look at an ideal whose depth, whose associated graded ring has depth at least d minus 1. In particular, if Gi is Cohn-Macaulay, then we do settle the conjecture that all these limits of EI of Frobenius power of QD, they do exist, and they are written in terms of Hilbert multiplicity of smaller powers of K. So if you calculate EHK of a few powers, then you know the EHK of all powers. Yeah, that is the so for reduction number 1, it didn't require much calculation, but it requires no reduction. But when you put this condition, the reduction number can be very high. Okay. So the result about reduction number 1, reduction number 0, they are all consequences of this, because in those situations, this condition is satisfied. To take a stable ideal, then the associated graded ring is actually Cohn-Macaulay, and then the all Frobenius powers are also stable, and so this condition is satisfied for stable ideals, and one retrieves the earlier formula of for stable ideals. Yeah.
What if one neglects this condition of depth?
Pardon?
What if one neglects this condition of depth? Then we have encountered them.
No. We have looked at situations where depth is 0. Even then, it's formula is true. But we don't know. Yeah. All right. So when n is bigger than the reduction number minus d plus 1, then we have this formula. So the conjecture was that for large powers, the Hilbert multiplicity of large powers of ideal or alternating sums of these binomials where coefficients are these asymptotic values of inverse sample coefficients. So we identify when this formula is true. So it is bigger than or equal to Ri minus t plus 1, then this formulation. Okay, let me give you an example. Take this hypersurface x cube minus y cube z f3 xy z. Where it is this? This is one of those similarities you can recognize for this surface similarity. Take then in this situation, because of x cube being y cube times z, x is integral over the ideal which is z by y and z. So this is an ideal z by system parameters in this Gorenstein local ring. And this is a minimal reduction of maximal ideal, and you can check that the reduction number is 2. Okay. Even if reduction number is 2, the associated derivative ring is 1. This is all theorem of Williamson that reduction number is 2. It happens, for example, for local rings of hyperelliptic similarity. The reduction number of maximal ideal is 2. Okay, so there are very concrete examples. This is one of them. So when this situation, when this condition is true, then the associated derivative is Cohen-Macaulay, and therefore the previous formula can be. Okay. But we do it by hand. So this is Cohen-Macaulay for large Q, and we calculate the Hilbert-Booth multiplicity of k's power of maximal ideal. And for every k, we have this formula. So it involves EHK m and EHK m squared. Once I have these values, then we can calculate EHK of all powers using this formula. And you can then calculate the EHK of m. This was first done by Conca in '96. His paper on Hilbert-Booth's function of binomial, the ideal derived binomials. So he calculated the Hilbert-Booth multiplicity of maximal ideal. This was 3, and we can calculate EHK of n square. It is equal to this thing mod the defining equation plus the Q's Frobenius power of m square. And this is an ideal derived by these monomials. It is just this length, and this can be done by hand. It turns out to be 9q square. Okay, so therefore EHQ of m square is just divided by q square. Dimension is 2, so divide by q square. Take the limit, and this is 9. So this is 3 and this is 9. Substitute here. We have formula for EHK of all powers of maximum. One would like to do this in higher dimensions also. But when you go to higher dimension, the reduction number may jump. It may be more than 2, and then we don't know whether the associated ring is going or not. So, how much time? 10 more minutes. 10 more minutes. Okay. All right. So now let me come to his second question. Pardon?
Last line.
Yeah.
Is there any base field is
F3.
F3, so then relation with the square root of n or
So this is to
if it is instead of 3, it's P some base field F3 instead of FP.
yeah. So these computation will become different because of characteristic 3. Computing cube of sum is easy. And this is a cubic relation, so it becomes easier to handle. Especially what we are trying to do is this is an ideal generated not just monomials, but also we have this binomial. So we calculate its Grobner basis. So if you change the characteristic, the Grobner basis will change. So I don't know what will happen. Yeah. But I expect that for large primes, similar behavior should happen. All right, let me explain you the answer to the second question. Maybe I will skip this part. So this is the proof of under the depth condition, the Hilbert-Booth multiplicity of powers as a formula. But let me skip the proof. Go to one of his other questions. Yeah. All right. So take a Cohen-Macaulay local ring, and I is an M primary ideal, and Northcott proved that the E0 minus E1 is bounded above by length of R mod I. And if equality happens, then the reduction number is 1, and the reduction number 1 ideals are stable ideals. So stable ideals can be characterized by this equality. E0 minus E1 is length of R mod I. And for stable ideals, the computation of Hilbert-Cohen multiplicity was easy for the powers. Okay. So equality holds if and only if I is stable. And why do we care about stable ideals? Because if you have a stable ideal, we know their entire Hilbert polynomial, the Riesz algebra, social credit ring, fiber cone, they are all cone coded. So it becomes easy to deal with these rings. Lippmann and Tessier proved that all complete ideals in several local rings, or more generally pseudo-reaction local rings of dimension 2 are stable ideals. And so this is a big class of ideals, and when you have a stable ideal, so one would like to know using Hilbert-Cohen multiplicity when an ideal is a stable ideal, and towards this we know where the conjecture that take a Cohen-Macaulay local ring I is an M primary ideal, then I is stable if and only if the asymptotic value of the first Hilbert-Samuel polynomial of Frobenius power is EI minus ESPI. Yeah. So this exists. He proved that it exists, and he wanted to characterize stable ideals using this relation. Okay. If I is stable, then my earlier slides give you the formula that this is true if I is stable. So his question is, well, if this limiting value is EI minus ESPI, can we conclude that the ideal is stable? This is not true. So here is a counterexample to Spirog's conjecture. Take this simplicial complex, yeah, consisting of this triangle and this edge. Okay. So this is a one-dimensional simplicial complex. So phase ring will turn out to be dimension 2. Then take the phase ring is quotient of polynomial ring in 4 vertices, and these are the prime ideals of these 4 facets. Facets are the edges, and these are the prime ideals. So I have this quotient. And so dimension of the phase ring is one more than the dimension of simplicial complex, and one can check that this is a one. Okay. This is a reflection of the fact that this is what is called a shellable simplicial complex. This is a commutative condition, and when you have a shellable simplicial complex, the phase ring is always one. This is a two-dimensional reduced Cohen-Macaulay ring, and take the maximal homogeneous ideal. Then the multiplicity by usual by standard facts, multiplicity of maximal homogeneous ideal of phase ring is the number of facets. There are 4 facets here, so that is the multiplicity. And in this case, we calculate that the E1 of the Frobenius power over Q square limit is equal to C. Okay. So I showed you in earlier slide how to calculate the Hilbert-Cohen function of powers of maximum homogeneous ideal, this as an alternating sum. Okay. So using that formula, we calculate E1 of this. In fact, in any phase ring, the EI of Frobenius power over QD turned out to be 0. So this is equal to 0 here, right? So now, but this ideal, maximal homogeneous ideal, is not a stable ideal. So to check its reduction number, okay, one can of course calculate some minimal reductions here. But rather than computing the minimal reduction, it is easier to calculate the Hilbert series of this ring. Okay. And Hilbert series of this ring turns out to be 1 plus 2z plus z square 1 minus z square. And since R is Cohen-Macaulay, the degree of the numerator gives the reduction number of the maximal ideal. So reduction number is 2. So therefore the converse in the Spirog conjecture for stability of the ideal is not true in this example. So stability cannot be captured by EHK unless you put some more conditions. Yeah. All right. So I will stop here. Any questions? Yes.
The conjecture of quantum at some point, think the quantity has is there some heuristic
Yeah, difficult to say why it is happening. There are so many instances that the value of the is determines the structure. If it is 1, it is rational. If it is 2, then it turned out to be rational. So the values are determining the similarity, but that is a very weird case that the structure of the completion is completely decided. But that conjecture is not yet true. Only the inequalities.
How do they guess it?
Yeah, so if you browse through literature on Hilbert-Cohen multiplicity, you will come across many weird calculations. many space formulas using integration and representation theory, maximum modules. All kinds of things are used, and what goes, everybody has experience. They will explain. Yeah.
Sorry, I don't know your mind. But you can do it for varied things and then go for predictive variety. How does the invert from relate to lightness of man?
Lightness of
base,
Yeah, as far as I know, the flat deformations don't help me. I have not seen any computation.
does it remain the same
I don't think.
even under deformation?
I don't know. Yeah.
So that one can make it.
It may be highly sensitive to the. I mean, you have to first fix the prime characteristic. If the ideal becomes a monomial ideal, the invertible multiplicity can be easy. Like in phase A, the quotient, we go quotient by square root monomial ideal, and the invertible function was easy. So if your question had a positive answer, then even complicated things they have easy. But we know that the asymptotic values of other inverse coefficients are not necessarily zero. So they may not be preserved as well. But I would be surprised. Yeah, so but when multiplicity can behave in any way to go at section. And it will increase. Unlike multiplicity. Yeah, general hyperplane section does preserve the multiplicity. But it would multiplicity now. That's the first thing people try, whether we can use induction and take a section.
It's not like semi-continuity or anything.
So there are semi-continuity results for invertible matrices. So if I take a local ring and take a prime value and localize the ring at that prime value, the invertible multiplicity of the localization at a prime angle is less equal to multiplicity of invertible multiplicity of the ring. Yeah, and there is a semi-continuity problem. The paper of Spino where he explores semi-continuity property of invertible multiplicity.
Any more questions? On. And this again. We keep after 5 minutes because we lost some time in the beginning. From my side, Kolkata, and keep on moving to
I must thank the organizers, especially Suratno, to give me an opportunity to speak here. And thanks for the excellent directing on the campus. I'll speak on the title is should I write bigger or bigger will be better. The monic inversion principle, and I'll put in parentheses for modules, ideas, matrices. I'll go through these topics one by one. And this is a mostly expository talk, so I'll be speaking about classical results. So let me start with one result. So this was proved by, okay, so before that, as the abstract mentioned, let me just tell you that what do I mean by monic inversion principle. So suppose I have, so let P be a statement over RT. The rings are commutative Noetherian, and by RT I mean that this is a polynomial. Let P be a statement over RT. Assume that P subscript F is true, where F is a monic. Then P is true. So this is monic inversion principle. So let me set up some notations. I'll write R round bracket T to be S inverse RT, where S is all monics in RT. Okay, so now, as I said that I'll start with the classical result. Maybe some more notations to save space. So P projective R module will be written as P belong to PR. And P projective R module of rank N will be written as so this is a theorem from 1964. So R is local, P is a projective RT module. Assume that so instead of writing inverting one monic, I'm saying that I am using this notation. So if you take if you change the base, so P tensor R round bracket T, that is a projective R round bracket T module. If this is free, then Horace proved that P is free. Actually, he was in this paper. The main theorem was not this one. His theorem was to prove that if R is regular local of dimension 2, then every projective RT module is free. And there he needed to use this result. But this result had consequences in proving the so-called Sayre conjecture, or rather known as now Williamson theorem. So Sayre made the conjecture in 1956, and let me write this as a theorem of Williamson. So K be a field and P be a projective module, and every module is finitely generated term. Then P is free. Now, apparently, there was no connection between these two results, but okay, this was proved in 1976. But suppose you want to solve this problem, one obvious way would be to attempt induction on the number of variables. And that's precisely what was done. And to do that, and I'll show you how that was done. And to do that, Quillen and Suslin, they needed to improve this theorem, which is now called affine Horace. So simply R is no longer restricted to be local. Then same statement. So this was kind of the missing part of this proof of Sayre conjecture. Now, why do we invert monic? As I said, that to apply induction. So let me produce the other code as well. Okay, so proof of Williamson theorem. So one advantage I should also mention that, so observation, why should we invert monic? So number one that is that dimension of R is equal to dimension of R round bracket T. So if you are dealing with polynomial algebra and you want to reduce dimension, so this R round bracket T is the ring to go for. Other property is that R PID implies RT is also P. And similarly, if you take R to be a field, then you get the function. So proof of Williamson theorem. So let me take K to be PID. Now P is a projective R module where R is K, QR, P. Now take R prime to be K round bracket QR. So this is, as I said, PID. And this is contained in so let me write this as I'll write this as so this is A round bracket. So this is contained here. Now by induction hypothesis, P tensor R prime is free because I have one less variable. So this implies that P tensor AT1 free implies P free over A1. So this is the advantage of monic inversion. So now, whenever I give talk on this theme or monic inversion comes up, then I face this question that why does this method work? So actually, Horrocks' proof was a geometric one, and if you go to if you look at QI Lamb's book on this problem, then he explains that what geometric idea goes behind it. So it is actually taking spec RT and spec RT inverse, and they are kind of glued over spec RT inverse, and then one gets projective line, and that is extension of vector bundle over projective line. But frankly speaking, after that, the questions I'm going to see, I really don't know that how that geometric idea helps improving results on ideals, etc. So I really don't have much insight. This is a strong method, it works. So that's all. Okay. Now, as I said in the abstract, that I give a list of open problems. The Quillen actually proved a more general version of this affine theorem. So P is a projective RT module, and Q we are projecting R module. And suppose P tensor R round bracket T is isomorphic to Q, you can change it to change the base to R round bracket T. Then P is isomorphic. Or which we write as Q. And P is extended from R. So what is happening? You are taking one RT module, projective RT module, and you are taking an extended projective module. And if they are isomorphic after inverting monics, then they are isomorphic. But obviously, one would like to ask this question that what happens if we remove the condition that this Q is extended? So this is question 1. So let me give both the projective RT modules. Great. So obviously this question came to people's mind in 1976, but the answer to this question is okay. Yeah. Which one? This one. So
This and the left hand side.
Okay. So I have R to RT to R round bracket, right? So I'm taking this projective module. I'm extending the base. I'm taking this projective module, going here and then going.
The same, it's a product sign. It's a product R or that.
Yeah, you first extend it to R polynomiality, then go to R round bracket. So, and also note that this actually is more a general version of affine products which I wrote here. So, if let the Q to be free, which is an extended one, so then you get that version of affine. So, this question is open. Only answer was given by Roy when R is local and P has a summand of rank 1. So apart from that, there is absolutely no progress on this problem. So let me, so while we're at question 1, let me pose even stronger version of question 2. So for that, I need a definition. A definition of project. Yes.
Main question. If we consider Q as the R mod, the restriction of in the previous result of Williams result was saying that P is iso Q one. How this Q and this Q here relate to?
Which Q?
No, in that question, if I consider Q the R mod, the restriction of Q,
Okay.
and then the this tensor product forward.
Then problem will be that if you go to this, consider it as R module, then you will have something like Q mod TQ. And you don't know that Q mod TQ, if you tensor it over RT, tensor it over so this is an R module and not intended. When it is extended, it's isomorphic. A projective module P is called cancellative if P derives some Q isomorphic to P prime derives some Q implies P isomorphic. So you can cancel this part P. A stronger version of position 2. So P be a projective RT module. Assume that This is cancelled. Is P cancelled? So obviously this is open, the weaker version of that. Okay.
Even if the calculated P with any module, I mean, from pre-module.
Yeah, projective model. I'm mostly talking about projective model.
No. Q is also.
Q is also projective. So now I'll slowly move to ideas. Before moving to ideas, let me talk about another problem on projective model. Going to the stop.
One-dimensional ring are still open.
Which one? Oh, one-dimensional cancellation always works. Or if you take a kind of a line bundle, cancellation works for line bundle, projective models of rank one. But I should have mentioned that. And I'm trying not to get into the dimension in comparing rank with dimension. So you know that if I have a projective RT module, dimension of R is D. Any projective RT module of rank, at least D plus 1 is cancelled. Okay. So now we need a definition. If we a projective R module, we say P splits. So this is not a standard term. I'm just using for this term. P splits. If P is isomorphic to Q direct sum R for some Q. And you can see that Q is also a projective R module. So by P splits, I mean that P splits a free summand of rank 1. Now, one idea of solving state conjecture was that suppose we can find some condition so that P will successively split P summand. So P becomes Q direct sum R. Then suppose that condition also applies to Q, and Q splits another free summand, and then eventually it will be. So interestingly, long after state conjecture was proved, Lindell gave a proof using that idea, and which is independent of Williamson. So I'm trying to tell why this P splits. This question is kind of important. Now, Most Reitman, he proved in 1979 a result which we believe a very important result, but instead of writing as a theorem, he wrote it as a lemma. He proved that if R is local and P projective RT module, assume that there exists an RT linear surjection where I is an ideal containing a monic. Then B I would like to rephrase this result in the language, in the notation I am writing. Is that so? Rephrase version. So R local, P projective RT module, P tensor R round bracket T flips, then P. Then obviously one would like to ask this question. Question 3. So can we remove this local R general commutative Noetherian ring? So again, this question is open in general, but fortunately, there were some progress. So I'll list some results. So this question 3, the known results and all affirmative results. I'm not writing that. I'm just writing the cases. So number 1 is that dimension of R is equal to D, rank of D is equal to D, and R contains an infinite so this is due to hot water burn and drying. And so not much is known about lower rank projective modules. Again, some partial result with some restriction on the ring. So R is regular containing a field, and I think containing an infinite perfect field. I'm not sure, but perhaps that was the assumption. Regular containing an infinite perfect field. Dimension of R is D. Rank of P is equal to N, where 2n is bigger than or equal to P plus 3. And you have seen this found in Dinna's talk yesterday. It all comes from the same kind of source. So then it was proved by whatever So here note that R is regular containing a field. So the projective module is actually extended from R. Now, very recently, for lower rank, we have been able to prove this. So this is dimension R is D. R is affine algebra over FP bar. And P is a stability RT module of rank D minus 1. Now, what is stability? Stability means that P directs some free module. So stability, that is P directs some RT some in size one. So this was so this results Partner Raja was in 2000. Was in 2003, and this has been proved by my student Banerjee and myself. It has not been published. But let me just erase this one. Otherwise, we'll bore the book. So now I move to ideals. And yesterday, Sudarshan was asking a question about the connection between the splitting. I talked about splitting and some generators of I mod I square for an ideal to be lifted. So let me make that connection so that we can move to ideals. So I covered modules. Now I'll talk about ideals. So first, connection between modules and ideal. So this is a consequence of a result of Heisenberg inverse is that if P is a projective R module of rank n, then there exists an R linear map where ideal of height same as the rank. So this is kind of a way of moving from projective module to ideal. Now consider the following situation. Dimension of R is equal to n, which is also equal to rank of P. And suppose I have an height of I equal to n. And for simplicity, I am also assuming that the determinant of P is trivial. So then, okay, so choose some isomorphism and fix. Now, this will induce P mod IP to I mod I square alpha tensor R mod I. And note that dimension of R mod I is 0, and that will imply P mod IP is free. So P mod IP is a free R mod I module of rank n. So choose sigma bar such that sigma bar, if you take weight, that is equal to I. It is compatible with I. So then what happens? If you take this composition, you get a set of generators of I mod I. So this composition sorry. Now, Atwadakar Raja proved that the splits if and only if. So let me call this as omega I. Omega I can be lifted surjection, call it theta. So what does it mean? So suppose this information gives me I equal to some A1 into AN plus I square. And theta will mean that I is equal to some B1 into Bn, and lifting means Bi minus AI belongs to I square for small I. So that was the connection Sudarshan was asked. So from here, looking at questions on projective modules, one can manufacture questions on IT. But I'm saying manufacture. That always it does not work so nicely, or you cannot expect to derive results on ideal from the theory of projective module. The reason is that, for example, if you take real 3 sphere and take a real maximal ideal, then it is known that on real 3 sphere, the rank 3 projective modules are all free. And then you know that the real maximal ideal is not generated by 3. So therefore, you cannot expect it to be image of a projective module. So if an ideal is projectively generated or image of a projective module, then obviously you can take advantage of this theory. But in general, they are not. And that's why that is an independent study. And sometimes this problem is more difficult, sometimes that problem is more difficult. It depends on the context. So now, with the previous questions in mind about splitting of P and the question of this Reutemann, I will say question of Reutemann, that was the local version. So we can ask the following question. The question probably 4. So I contained in RT an ideal. Let me take dimension of R is equal to E. Height of I is equal to N. And again, I'm putting this restriction which comes from Mohan Kumar's result, which Tina talked about. And assume that I is given to be say F1 into Fn plus I square. And assume further that if you go to R round bracket T, then you can leave. So assume that this ideal to extend to our round bracket T, this is equal to some G1, G2, Ga, where Gi minus Fi is the I square around T. Then can we find F1, F2, Fn I such that I is F1, Fn and Fi minus small fi I square. So this is the first question about I. I mean, for me, the only question about I. And okay. So this was actually given to me by Bhattacharya while I was doing my thesis back in 2000, 2001. And I could not solve this problem exactly. At that time, I could, so let me write down the known cases. In general, this is open. So one is R semilocal. Number two, R is affine over a field algebraically closed and characteristic A equal to K. So these two I could prove in my thesis in 2003. Then I tried this problem for quite some time. And eventually, after a long time, in 2008, I must say that these two results are proved when D is equal to K. In 2018, myself, they are my former students. We have been able to prove when R is smooth affine over an infinite field K, where characteristic K is not equal. And this proving this result, it took a huge effort. We had to use the quadratic forms and orthogonal groups, etc. And that's why you can see that characteristic is not equal to 2 assumptions. And surprisingly, so recently I have become interested in studying affine algebras over FP bar, which is somewhat easier to work with because of some reasons, and sometimes also difficult to work with because the kind of methods we use, you may lose the structure that an affine algebra. So let me not get into the details. is for n equal to p, and R is affine over S bar. You see that R is affine over an algebraically closed field of characteristics equals to R here, and this is for affine over S bar. So in general, for any algebraically closed field, we still don't have that. So since I said that modules, ideas, and matrices, I'll just quickly mention some results on matrices. And since there is no proof, I can just write them down. Now, recall that the elementary subgroup ENR is the subgroup of G ln R generated by elementary matrix. And so in proof, if n is bigger than or equal to 3, ENR is normal. Now, Suslin also proved this monic inversion result. It was again long back. N is bigger than or equal to 3, then we have this natural map. Go to round bracket T. Using G. Now, this elementary subgroup, they have been kind of emulated in various other branches, like people talk about Chevalier groups, etc. I don't know anything about them, but I know that a similar result for Chevalier groups was proved by, I forgot, I think Stepanov. So Russian mathematicians, so there are some people who work with Chevalier. And if you think of the result I talked about projective modules, affine Thoron's theorem, if that was about K0, so this is about unstable K1. Unstable K1. So I'll mention one result by Anastasia Stavrova. So I'll just give a special case of this one. So consider the quadratic form and let O2n plus 1 R be the corresponding orthogonal group. And there also you can talk about its elementary subgroup. So Vavilov gave explicit description of that elementary subgroup. So, and I think there was a paper by Amit where he describes the generators of this group. Is the elementary subgroup which is an analog of this EN, elementary subgroup of GLN. Then Stavrova proved in 2014. She was also studying some non-stable K1 functors for objects like some very general objects, not mentioned. So she proved that O12 plus 1 or 3 over and in a sense, we used this result to prove the result I erased, that my result is Tikadar and Pinta. So this is indeed. Huh? Oh, it requires a long list. Okay. So like you can, in the linear case, you can define the GLN as the subgroup, elementary subgroup they are generated by Eij lambda. You can easily describe that. At ij place, I have lambda I not equal to j. Diagonals are 1 and everything. But this requires some description. It is generated by 5 types of matrices. If you want, I can show you. So there is a paper by Dandilov and it describes how. Description is also quite interesting. So now these groups are coming up into various questions, like in works of Fazil and Arvind Ashok. They are studying now. So this one. So I also wanted to talk about unimodular rules, but let me skip that. I don't want to stretch it. If one is familiar with unimodular rows, I will just write the open question and stop. So a row, so again R is a ring. U in Rn is called unimodular. If there exists another row such that, so this is unimodular of length n, such that U T transpose is equal to 1. And UMN R, the all unimodular rows of it. Elementary subgroup, actually GLNR, SLNR, they all, it acts on UMFR. You take something sigma from here and you take U from here, then sigma. That's that. Now, let me take UW n bigger than or equal to 3. And so orbit space, the set of all orbits under this action, I'll write this as UMNR slash EMR. Or all elementary orbits. So they're connected by elementary. Assume that orbit of Q and orbit of W are same in round bracket. I'm using the same notation as W. So again, now if known for special case, if you take W to be the unimodular row 1, 0, 0, Q1, then it is known that is due to Ravi Rao. That's a great flavor. But in general, if you take two unimodular rows such that they are connected by elementary matrices over R round bracket T, then it is not known whether that
Any questions?
If you take an algebraically closed field and if you take top height I here, say I, such that I is local computation. Suppose I mod I square is generated by T, then I is image of it. And that I mod I square, it comes from a certain conversion.
Any other question?
This last topic that we discussed about detectivity and modular rules. And one, the translation in terms of project to project.
Yes, because unimodular rows are stably different, right? So you can translate them. But I think it is much more easier to work with unimodular rows. You have a lot of freedom.
Previous one, either asking or
Oh. So that is, you are asking for any projective module analog. It is in K1, so I have used the K1 concept.
Any more questions? Again. Yeah.
for the invitation. This is my second talk in this series. One in the 2021 was in virtual, and this actually here. So very nice arrangements, I must say. Okay, so let me start. So I stop around within 1 hour. Yeah, sure. Thank you. Okay, so this one is this you will see that these are the sections, but mostly what we will do is we will try to generate some questions, and it's kind of an ongoing experimentation with these questions rather than answers to the questions. So in a process, of course, there are some observations which are interesting. But if you really ask why does it happen, it's very difficult to answer yet. And principal part of it forms the thesis of Pranjal, who is present here, and joint work with. It's a kind of work that we have been doing for last few years with my students. Okay, so this was the abstract. And as I have mentioned, that it's with Joydeep, Ranjana, Pranjal, all of them are present here. Om Prakash is not here, Priti is in. So what we are trying to do, this is not something new, because Professor Patil is sitting here. He is an expert on this and asking questions like what happens when you pass from the affine to the projective closure for these kind of cases like numerical semigroup rings, what properties are retained? That is the principal question. And we see that it is very difficult to give a very consolidated answer to this. But so, as I say, it raises many questions and we still don't know why it happens, except for some algebraic way to look at it. So, okay, so let me set the background. Why we suddenly embarked on this question. So this is probably due to Kronecker, the 19th century, that this question you all know, I'm sure, that if you have a prime ideal and then you know how many number of generators are required at least, and you are asking whether there is an upper bound on the minimal number of generators. And this answer is obviously no. That was known. It is not something that is new. And it was known through various examples, but you will see a very interesting common feature in all these examples, which kind of initiates this study, which probably has initiated this study for many authors, many mathematicians. So Macaulay's examples come first in 1916. I believe that is concise treatment is given in that book written by him. But there were certain questions or certain gaps, and which were completely resolved by Abhyankar in 72. So Macaulay made many claims, but it was not very clear that how to prove those. Claims happen to be true eventually. And Macaulay's examples are the first one where he is giving a family of prime ideals in the 3 space. And they require this kind of at least R generator. So you can see that you do not have any upper bound. This is the first example probably that exists.
Family, all the ages are like,
Yes, yes. Yeah. So then a detailed explanation of Macaulay's examples. And then interesting enough, around the same time, this, okay, so then there was the question that what happens when you extend it to the power series ring? And there was a suggestion by Hofstede, as mentioned by Mo himself, that if you just take Macaulay's example and take them in the power series ring, this might work, but it doesn't, because they can become, reducible. That's the problem. So McMo's examples are different, of course. But what I said is there is a kind of a common behavior in all these examples that they are all not just rational parameterization, but monic parameterization, monomial parameterization. And Mo just tweaked it a bit. But how the idea came about, it's very difficult to say, because that is not revealed in the paper at least. but most examples were almost monomial parameterization, except for just a little change. Okay, and he saw that no, just extending Macaulay's example doesn't work. So it is a different set of examples, and he has these two work where he is giving very precise statements. He is also saying that it has determinantal structure and things like that. And interesting enough, in much later, of course, during when Ranjana was doing her thesis work, we could show also that with when Ranjana that there is a precise algorithm you can create to write the generators and show that it can make it completely constructive, that this indeed requires unbounded number of generators. And around the same time, as you can see, that Brzezinski is giving again monomial parameterizations and giving a family to show that in the affine 4 space you have a family. And then the story in a sense ends here, because once you have given a family in 3 space, 4 space, and so on, in higher dimensions, you don't have to do any other work, because you can simply treat these other variables as dummy variables, and you have your examples in any embedding dimension. So Kroneker's question has been answered. But truly speaking, if you ask that, no, we want something non-degenerate in any embedding dimension, then that example was not known. So till date, I would say it's not known. So the thing is that this simple process of just extending it in any dimension by, actually, soon I will come to that notion. There's a notion called gluing of numerical semigroups. So this is actually gluing by the natural numbers. And that immediately creates your examples in the higher dimension. But I wouldn't really say that it is really living in that arbitrary embedding dimension. So that example, we do have a conjecture, but proof is not known yet. Okay, so this is the beginning, and this is celebrated. I think any numerical semigroup talk is incomplete if we don't mention Kunz's results. So how numerical semigroup naturally comes into the picture is from this question asked by Zariski based on Herzog's thesis. Herzog is the first person who kind of get the complete picture in embedding dimension 3, and then there was this question asked, and then in fact it's Kunz who showed that if you look at the curve and look at its value semigroup, that happens to have some speciality, and the value semigroup reveals a lot, and in fact the Gorenstein structure can be read from some particular behavior of the value semigroup called symmetric, and so on and so forth. So you see, this is the story, but now people look at it from 2 different perspectives. One is just take this numerical semigroups as an object and see it, I don't know, maybe solve some Diophantine equations and do something. Another is looking at it from this Kurt's perspective and try to understand the numerical semigroup, go back and forth. Okay, so this is what we are sort of trying to do. So the questions, if I have to set, so let me run through some basics, because if in case you are not familiar, then these are meaningless. So concepts are very simple. So usual notations, and this is what we call a submonoid. That is a subset of the set of natural numbers if it contains 0 and it's closed under this natural addition. And it's called a numerical semigroup if it is finitely complemented. So that means the submonoid whose complement is finite. So I'm now just introducing the numerical semigroup, and then we can tie it up with the Kurt's thing. So you can write many such examples, of course. This is I've just written one such. A few terminologies. Now, these are some basic properties. If you take any basic book on numerical semigroups, you will see that these are listed as some lemmas and propositions and whatnot. One can work on it. It's not difficult. I mean, it's that a numerical semigroup always has a unique minimal generating set. So you know what it means by a generating set. That means some integers whose non-negative integer linear combinations gives you that numerical semigroup. Then a submonoid is a numerical semigroup if and only if the GCD is 1. And every non-trivial submonoid is isomorphic to a numerical semigroup. So these are, with a little bit of work, you can work it out. It's not very difficult. Okay, so but this is through this, yeah, that's exactly what I was saying. What do you mean by these generators? That means the semigroup base, the numerical semigroup base can be written as a integer linear combination of these numbers, and 0 to any minus 1. But I don't know if you have heard about it. This is something very interesting. This is called the coin exchange problem. That you can also see it as some denominations n0 to ne minus 1, and you are asking whether there is any value which cannot be, which you cannot recover through these denominations. So this is what is called the coin exchange problem. Of course, you need to take this to be n0 to ne minus 1 should have this to be 1. Otherwise, this is not very meaningful. So in terms of numerical semigroups, the question takes this form. Does there exist an integer n? Sorry, I mean n, not n0. Does there exist an integer n which is not in the semigroup, but every integer n plus 1 onwards belongs to the semigroup? Okay, so whether you do have, actually it's a slightly modified version of that question. You are happy if you can answer coin exchange if you have one such n. So that's the question. Do you have one such? Well, it is true because the numerical semigroup by definition is finitely complemented. So that means there are only finitely elements falling outside the semigroup. So there has to be a maximum element, and that is the n. So answering that coin exchange problem is not a difficulty. So the answer is yes. But obviously the question which people would ask, and to know that I will give you the denominations, you will tell me that amount which cannot be recovered. Sounds pretty simple, but it's very hard. And the computer scientists have spent a lot of time to understand the kind of T versus NP problem and the hardness, etc., the complexity of the whole study and so on. So the whole, and so some terminologies quickly. So that number, which is the largest and not belonging to the numerical semigroup, is what is called the Frobenius number. And onwards, everything belongs to the numerical semigroup. That is called the conductor. As you can understand, the name has been, this name is probably motivated from the geometry rather than pure algebra or whatever you call it. Okay, so, and as I was saying, that Kunz's observation is something very, very significant, where he's saying that the symmetricity of the numerical semigroup gives you the Gorenstein property. So this is the symmetricity. So if a numerical semigroup has the behavior that something onwards, the conductor onwards, everything is there. So before that, if you have exact matching of the numbers which are in there and outside there, so then you call it symmetric. So so Kunz's paper is indeed wonderful, like how this kind of thing is captured through Gorenstein, etc. But anyway, these numbers will be a little meaningful for us for at least next few slides. And the number of elements which are outside this semigroup, this is called the genus. And the number of elements which are less than the Frobenius, but inside the semigroup, is denoted by this number ns. So these are some standard notations. And here, the first, so this is called the linear Diophantine problem of Frobenius, that compute the Fs, the Frobenius, and Gs, the genus, in terms of the generators n0 to n-1. This is a question which is in general very hard, and I do not know whether people are still sort of trying to give an answer to find an expression in an obvious way. Rather, I think people are more interested to learn that, I mean, more about the solvability of these kind of questions, right? But what interests us is its connection with the curve and its projective closure and its length. Sylvester's result, you can see 1884. So it is probably, it will not be correct to say that the whole numerical semigroup study started with Macaulay's example. So probably there was something more to it. Probably the Diophantine equations kind of questions. So these are the first few observations, as you can see, for two integers a and b. If you take the numerical semigroup generated by a and b, they are co-prime integers. Then your Frobenius and the genus, they have this kind of an expression. This also it's nice, it's very interesting. But the moment you start with three integers, the situation becomes really difficult and different. Okay. Okay, so yeah, Selmer's result. This is another notion which is very, very important. I mean, if you look at all the work, significant work done in numerical semigroups and things like that, So you will see that they always try to understand this very special set called the Berry set, which are kind of the integers which are giving you enough information about the generators and many other things. I'm just saying it in a very sketchy way, okay, instead of getting into details. So, and here again, you can write that Fs and Gs. By the way, this is a pretty general result. I mean, like here, it's not restricted to just two generators. That you can write the Frobenius and the genus in terms of the Berry set. And this is the expression. So obviously, you can understand that. So it's finally a finite calculation. But writing the Berry set is hard. It's not easy. In fact, it's very hard. So therefore, the problem has not been. I mean, it has not been simplified way, but it is a good way to look at it because your whole searching is now within this Berry set. If you can write the Berry set, then you know a lot. In fact, you know almost everything about a numerical semiconductor. Okay, so yeah, some examples. And by the way, this is the conjecture which I know very few people who are working on it, and that too with a lot of restrictions. But otherwise, it is open, mostly open. I mean, like I do not know any significantly good results. So this is called the Wills conjecture. So it is giving an upper bound of the Frobenius. So the Frobenius, again, the whole thing is connected to this linear Diophantine problem. That whether you can write the Frobenius in terms of the generator. So it's not in terms of the generators, at least in terms of this. E is the embedding dimension. That means the number of minimal number of generators you require for the numerical semigroup. And NS, you remember, this was the definition. Let me just take you slides back. So this is those elements in the numerical semigroups which are less than the Frobenius. Okay. So giving an upper bound is, of course, a natural way to go about it. And this is a conjecture, again, surprising enough. How Wills came up with this conjecture, there is no kind of a very detailed or even a kind of a short description that is it motivated by geometry or is it just a sheer calculation. But so far, people have some examples supporting this, but do not have any counter examples. But again, the problem is there are not enough examples known because it seems to be very, very hard. So finding an upper bound, and I know recently I attended a talk where the researcher was saying that one way to see is that look at the difference and approximate it. Okay, so approximate it in a good way. So of course, again, I'm being very sketchy, but that sounds like a very reasonable approach. But again, he himself is not very hopeful that that will give a wide class, but at least some classes can be understood through this. Okay, so we will come back very briefly to this conjecture at our last slide. So let us now, yeah. So as I say that once you have a numerical semigroup, this is the obvious way to create a curve out of it, that is through this monomial parametrization. And all those examples starting from Macaulay with C and things like that, or whatever which has been generated to answer Kroneker's question happen to be kind of somewhat monomial or completely monomial. So that's the interesting thing. And you have this monomial parametrization. And this is the question which is again very much open, that you start with for an arbitrary embedding dimension E. Suppose you have a numerical semigroup which is symmetric. So you know Kunz established the fact that symmetricity of the numerical semigroup is connected to the Gorenstein property. So if you cannot get some good proofs of good results for as nice as Gorenstein cases, the general case would be much, much harder. So here the natural question to ask would be, can you say that so what is Pn? Pn is the kernel of this map, this affine K algebra map, and then whether that minimal number of generators has an upper bound, which is a bounded function of it. Okay, but this question is also absolutely open. And very recently, again, there is I had a chance to attend one talk by Professor Watanabe, and he was again giving a different method to look at it. Once again, we don't know, but there is some kind of a technique to look at it, and hopefully that might reveal more information about it. That for a symmetric numerical semigroup or a Gorenstein affine monomial curve, do you always know that the minimal number of generators is bounded above by a bounded function by delta? Okay, so these are the few questions which kind of set the background for whatever we are doing, whatever we are looking at. And yeah, so now the question is, so these were the question examples that were known in the literature, and we kind of tried to see, most of these are you can't possibly do them in a very basic tree approach. So you have to start looking at the generators, try to see, and like it's kind of very tedious calculations, often leading to Grosvenor basis techniques and things like that. So we saw that, of course, Brzezinski's example, which existed from 1974, and then two more examples, and all of them are done from different perspectives, by the way. They're looking at tangent cone and things like that. But all of them have the common feature that all three examples are in affine four-space monomial curves, and they have the unbounded number of generators for their defining. Okay. So we were trying to see that, okay, fine. I mean, like somehow they have proved it. But what kind of common features, do they have any other commonality? I mean, like what happens when we go to the projective closure? What about their higher Betti numbers, which was like another question, because Kroneker's question is only about the minimal number of generators, but that is the first Betti number. What about the total Betti sequence? Do you still have unboundedness? So for the first class, that was the answer that yes, it is in fact that you have unboundedness of the higher Betti numbers as well. But is it a very conclusive thing? Whenever you have unboundedness of the first Betti number, you know for sure that happens for the higher Betti numbers. Again, that's not true in general. So we will see some examples there also. The moment you go to the projective closure, different things might happen. Okay, but this is the common feature. So this was the sort of starting point. So to see these curves and try to understand them as much as possible. And yeah, so what we first saw is that, which is a kind of natural temptation to understand whether they fit into one model. Probably they don't, I don't know, but definitely Brzezinski's example can be actually understood by a slightly more general situation like this, that what you do is you take two string of arithmetic sequences with the same common difference, but their starting points are different, and then just put one after the other, and in such a way that this b minus a, the difference, cannot be divided by e, so that you cannot complete it to one full sequence. So if you see all these examples carefully, they do have this kind of a pattern roughly, especially Brzezinski, and what we call concatenation and things like that. And interesting enough, this really gives answers, yes, I mean, like the counter examples to Kroneker's questions. And as I said, in arbitrary embedding dimension, it is still not known. But this would be the conjecture that this is the family which probably has the answer that which requires minimal unbounded number of generators. So, but beyond 5, there is no proof yet, and I do not think that this is a reasonable way to go about it. Like proving these things for each embedding dimension throws a different kind of challenge. So, how do you go about it? We don't know, honestly speaking. Okay. So, but anyway, this seems like a very reasonable example where you do have any embedding dimension. You probably this would work. But if you are looking for a proof, then I do not have any proof beyond greater than or equal to 5. But definitely, this family gives some very interesting situations. I mean, it is not that always concatenation means a replica of Brzezinski or something like that. No, you can just play with the integers and create many nice families as well. But let us not get into it. Okay. So, yeah. So let me now come to the main part of today's talk. So this is how you define. So you start with e positive integers, and with the modest assumption that suppose the same e is greater than mi, so that's the largest one. And then you have a numerical semigroup, and then you create this semigroup in N2. So you have now moved to N2, numerical semigroup lives in N, which you define by these tuples. And then, or in other words, what you do is, this is how you do a monomial parameterization for a projective monomial curve, right? So that's exactly what you are doing, but with the help of those integers. And it is justifiable to call this the projective closure of the affine curve for the simple reason that you can see that the homogenization of the ideal M1, M2, M with respect to this new variable x0 is actually giving you the defining ideal for this projective monomial curve. And so what you are interested is in this affine K algebra, that is the polynomial ring quotiented by this homogenized ideal with respect to anything. Okay, so you are interested in knowing the properties of this K algebra basically. So this is the question. So what properties? So obvious questions like if you have the numerical semigroup is defining, suppose, by the way, where does it start? So numerical semigroup ring defines an affine monomial curve by this affine parametrization. By this parametrization, which is obviously Cohen-Macaulay. So that's the starting point, whether your Cohen-Macaulayness is preserved when you go to the projective closure. So that would be the first point to start at. And then you keep asking that if you have Gorenstein, that means if the numerical semigroup is symmetric, when you take the projective closure, is the property retained. Unfortunately, nothing is true. So everything fails. But we will just try to see some modest situations where it is really true, but you will see that actually none of these are actually preserved under the projective closure. So let me set the question first. Yeah, so I think I missed. Yeah, anyway, I wanted to ask it right here. So let me take you to that slide first. I think it has come somewhere later. Yeah, so these are the questions that first primary question is you have a Cohen-Macaulayness is always there for the affine monomial. It's a one-dimensional domain, right? So the moment you projectivate it, then whether you have the Cohen-Macaulayness preserved, that means whether that AX0 to XC quotiented by that bar of P, whether that is Cohen-Macaulay or not. Similarly, Gorenstein. So these are some questions. And what about the Betti sequence? So you saw many families with unbounded Betti numbers, first Betti number at least, or even higher Betti numbers. When you projectivate them, what happens? Is it still the unboundedness is preserved and things like that? So these are some natural questions to ask. And also, if you look at the question 1, which also happens to be a very interesting question, that there is a notion called gluing of numerical semigroups. So you have a couple of numerical semigroups and you can glue them by suitably choosing elements. Let me just say it roughly. And you can create a new numerical semigroup. By the way, I'm talking about numerical semigroups. I'm not talking about semigroups in higher dimension. Their gluing is not obvious. Their gluing requires some time. But just gluing in N, okay? And you can create them. So we were trying to understand, like it was kind of that suppose you have some niceties happening for the projective closure of the numerical semigroups, the respective numerical semigroups. By the way, you understood by an abuse of notation, I'm saying projective closure of numerical semigroup means that this gamma bar. So that is what I mean by this. So if you have some niceties of gamma 1 and gamma 2, and then you go to N2, suppose you have glued them, then what happens? I mean, then do you have some special structure? So what do you mean by special structure? Whether Cohen-Macaulayness is preserved or Gorenstein property is preserved and things like that. So what we have observed, so the experiment started with these examples. So these Brzezinski curves, if you remember, I showed you 3 curves, that Brzezinski, Bacalin and Arslan curves. And we were just trying to see what happens to them. So with some effort, you can actually write down and see that, yes, indeed, so that it has this still that, as you can see, the Brzezinski curve. It was in embedding dimension 4, right? In the affine embedding dimension 4. And here you see, so the last Betti number happens to be 1. So here you do not have the Cohen-Macaulayness. when Collinus itself fails. So it's probably a hopeless situation to even proceed further. But on the other hand, if you look at this curve, although they more or less fit into that kind of a model of concatenation, but if you see this here, you do have that, as you can read, let me point out the particular portion, that your projective dimension and everything is preserved. And not only that, you go to the projective closure and project with respect to x0 equal to 1, and you have your affine version. So why in this case it happens and not in the other case? A very reasonable answer would be we don't know, other than these calculations. And also for this, as you can see that here also, we can write down and unboundedness. But the interesting thing is, for the first Betti number, definitely the unboundedness happens for all of them. So that one you can't probably cut down so much that suddenly you will be able to work with much lesser number of generators. But other than that, we don't know. So it's pretty weird in some sense. Okay, so what is not weird is, so these are the three questions. So some kind of nicety is there, and that is why I said it is just experimentation with these questions. So the first question asks that if can you give some condition on the gluing, which kind of helps us preserve the Cohen-Macaulay-ness of the gluing property? Because we could see that it's absolutely is not giving us a much kind of information by looking at many examples. So it's not true that always the projective closure has some kind of nicety. So do they have any nicety at all under some special situations? So, and second question is, what about the Betti sequence? Can we say that they match? So looking for sufficient conditions, I would say. And what is the connection between the Cohen-Macaulay-ness of the tangent cone at the origin and the arithmetic Cohen-Macaulay-ness of projective closure? So this is also a third question, which is still not so well explored. But the first two questions, there is some partial observations. So as I was saying, this is the notion of gluing. So if you just let me point out two particular portions. So you are basically starting with two numerical semigroups and gluing them with respect to two elements P and Q, coming from two gamma 1 and gamma 2, such that they're GCP1. And you have the assumption that you are P and Q, they avoid these generating sets. And as I have written like this, is this the no. Okay. Yeah. So if you choose your P and Q carefully to avoid kind of degeneracy, then this is called the glued semigroup. So you have this Q multiplying Q by, or rather multiplying all these generators M1 to Mn by Q and multiply all the generators M1 to Q by P. P has come from gamma 1, Q has come from gamma 2, and this is called the gluing. And then the gluing, you can very easily see that this doesn't change much. The behavior of gamma 1 and gamma 2 are retained. You just need one extra generator in the minimal generating set of the glued semigroup. So this is obviously a very good situation to look at, right? But unfortunately, even for this kind of gluings, unless the gluing is an obvious gluing, but or rather a very trivial gluing, so this kind of gluings also are not always very sure that niceties happen. Okay, so this is a very special gluing you can see down below, that where your P is a kind of a simpler expression. And for that, you will see that there are certain good things that happen, which you are calling the star gluing. And this is the result here.
Gluing at the ring level is second.
No. So it's just taking one extra generator. In fact, this is the reason why you say that when you are trying to define a gluing in a similar way for N2, then you have a lot of trouble, because there it doesn't conform always with these conditions. No, this P does not belong to this, and does not belong to this. So what you can imagine is, it is that sort of a union of all these hypersurfaces together with one extra one, which is negating the relation between. No, it's not secret product. Okay. Okay, it's much simpler than second order, but still, it's not really, the results are still not very encouraging. But in this case, at least, this is the result that if you have two numerical semigroups such that their projective closures are Cohen-Macaulay, now under this, you are gluing at the n level, please remember, not in the n2 level. At the n level, you glue them and glue that through special gluing where P is a much simpler one. So this is the special gluing, okay? And there, which is involving just one generator, as you can see, and with this condition, then you do have that, sorry, you do have that the projective closure is also an arithmetically good Macaulay. And also the Gorenstein, you have a similar result that you have this gluing, the special gluing, then that is also preserved. So at least some nice situations where you can create many, a natural way of creating many Cohen-Macaulay or Gorenstein projective monomial terms. Because getting them in the affine level is not very difficult. You can create many because you can create many symmetric numerical systems. But then creating them in the projective level is naturally a hard problem, but this at least gives you a family. That's the merit. Okay, and did it change? Yeah, I asked that question about Betty sequence also. So here is also some observation that with some modest condition, you can actually, so you see, I mean, translating these, you can ask all these questions, but translating these at the K-algebra level in terms of Grobner basis and things like that is always hard. So how do you actually come to something which is sort of tangible and which you can use to study these? So luckily here you can, and you can show that this project Betty sequence for the projective closure and the affine curve, they do match under this kind of a situation. And this in fact spits out this corollary as a special case that if you have an arithmetic sequence, then for this the projective closure for the Betty sequence for the affine curve and the projective closure, they do match for all. So you do have some situations, but the question again is how restricted it is. So, or rather, going into the deeper one, can one understand them geometrically? That is what I definitely don't know. Okay, and this is another observation, a quick observation. Once again, so the gluing in this case is even simpler. That was a simpler gluing in the sense that one of the elements was simpler, but here you are just gluing with respect to n. So that's exactly what I was saying at the beginning, that that's another natural way to create curves with higher embedding dimension. But interesting enough, that doesn't always ensure that the projective closure would retain everything. But here it does, that at least you can say that if you take a gluing with respect to n, which is being called a simple gluing, and you with your choice of C and E, etc., some technical conditions, you can see that you do have the Cohen-Macaulayness is preserved under projective closure. And so you can say the type, I can't write Cohen-Macaulay type because they are not Cohen-Macaulay once you go to projective closure, but the types also match and things like that. So this is like some best cases that at least we have come across where something can be proved. Okay, and now just one quick last observation. So this Wills conjecture, if you remember, that was trying to give you the bound of the Frobenius with respect to that in what we defined and the embedding dimension. So here you can in fact ask a generalized Wills. So an extension of Wills conjecture nowadays, it is called generalized Wills, because interesting enough, when you go to N2, there the generalized Wills, although it doesn't make sense always, but under suitable conditions, you can ask that question, and there probably more examples are known. So you know what is difficult in one dimension, probably slightly simpler in N2, which usually doesn't happen, but in this case it does. And here you just have to be a little careful. You have to take, because in N2 it is no longer finitely complemented. The numerical semigroup is finitely complemented by definition. But once you go to the N2 thing, then it may not be, complement set need not be finite, but you can have this condition. I have not explaining it in detail, And there you can sort of write it a little carefully. That this G set, you can see that elements G in S such that G less than Fs. So of course you have to define a suitable ordering there because you're working with the vectors. And the count of that is exactly your N, right? Rather NS. ES is the embedding dimension, and then you have this. You have to define this Frobenius because everything will come as vectors there, right? So you have to define them carefully. But you can define it, and then the question was whether extended will holds. But unfortunately, this question cannot be asked. It doesn't make sense that if you take a numerical semigroup and then it takes projective closure, your this will question does not really make much sense. But at least this is one recent work with Om Prakash and Priti, where we could see that this kind of conditions with these definitions of symmetric and pseudosymmetric semigroup and the extended will fold. So you do have some families, but these families, unfortunately, they can never come out from a projective closure of a numerical semigroup. No chance for some obvious reasons. But at least one can ask this question that if you have a numerical semigroup, and suppose it satisfies will, so you have a very nice bound on the Frobenius, then what can you say about its projective closure? The wills, yeah. So yeah, this one.
Since the local sign is changing.
Oh, really? Oh, sorry. Yeah. Yeah, it's an upper bound of the Frobenius. Yeah. Oh, sorry. Yeah. Yeah. Okay. Yeah. Thanks. So, yeah, the question is now rather, it's a different question altogether that studying wills in N2. But because this cannot really be directly connected to the projective closure of numerical semigroup, but at least one can ask this question that if you know gamma satisfies this, then whether projective closure has some significant some significant properties. But unfortunately, I know of only one good family of numerical semigroups which satisfies will, that is the one defined by arithmetic sequence. And for that, we know that all good things happen in the projective closure. Petty sequence is preserved and this and that. So other than that, we don't even know much families really. So therefore, this question also has its limitations because at least in this kind of study, you would first try to look at many examples to get some good idea. Because otherwise, you can't just stare at the results and imagine something. So unfortunately, the first question still boils down to the Wills conjecture for numerical systems. But of course, I mean, like, again, this is a very random question. But based on this observation that there are good families in N2, by the way, which satisfies it will, and especially this kind of concept called systemic group, which is not very old, like, and people do it. Okay, I think some papers which we have used. Thank you. Issue. There's a paper by Shalom Eliyahu with the number theory. So he has some conditions. I don't remember the technical ones now, but it's still not like a kind of a very wide class. So I would still say the best is that arithmetic sequence that satisfies me. So the proof is very nice. Actually, here, so far as I know, only the number theorists have taken a try at it, and they have tried with the continued fractions, as I was telling you. So it's the continued fractions, which is as basic as this, but it produces some wonderful results. So I still believe that would be a very powerful thing. Yeah, better than that, I don't. At least I have not seen much results.
Very basic. So in the configuration of the group, right? So the symmetric semigroup. So those numbers, those are not semigroup. I mean, they are
does it appear in the numerator of Hilbert series?
Does it have what? Any
Appear in
effect
the
on this?
Hilbert series, numerator of Hilbert series, right? Going to mix together.
In general, is there anything I don't?
No, I'm just asking, does it appear?
No, what appears? You mean
So,
those numbers?
Those
and-
numbers are there, they're symmetric, right? So somehow, and the H vector we have. for
Yes,
Hilbert, right?
you have the
It's symmetric.
symmetricity. Yes.
Somehow, like these two,
They will appear.
It appear, but how, whether that helps you understand. I mean, but however you calculate the H vector is always a challenge.
yeah, right. So that's what I'm saying. Like,
Oh, the whether they show up?
Yeah.
Yeah, that thing.
oh, okay.
But probably as Professor JKV was also pointing out in the morning, that if you were trying to calculate, say, any multiplicity or these kind of things, that itself is a challenging thing. So yeah, after you do that, they show all sorts of nice things. Yeah.
Yeah, the residual property can be read off from the numerator because it's a one according to the.
Right, but after you have written that.
After that,
Yeah, that's exactly what it is. After you have written that, yes.
Stanley did for the way after this. Stanley still for up to like 10 years of right? But
Yes, but Stanley, of course, I mean, he gives this kind of an expression that he says that if this happens, yes, of course. Yes.
so that was the question, like, does it actually, so we have a nice symmetry there in the center group.
True.
Will it show up?
True. Numerical symmetry.
what about the we preserve and the
The result I know is by Thoma, who created set theoretic complete intersections in projective space using a kind of doing which is not calling doing here. But whether it is preserved, I don't think it has studied. Yeah, coming from the projective closure.
Yeah, if they are set theoretical complete intersection, then the weed process keep it.
Yeah. That is one particular case, yes. Yes.
Weed will also keep set theoretical.
Yeah. The generators are very explicit in blue. So it is just one extra chap which shows up and that you can write very clearly. Yeah.
Any more questions? Not time to speak again. So, this is an announcement here that is a photo section near the entrance of academy.